Hey guys, today we're going to learn about Newton's law of universal gravitation, and we're going to get into the inverse square law. So last time we learned about Kepler and Kepler's laws, and I may or may not have mentioned at the end of that. The reason that we care about Kepler's laws is because Isaac Newton, when he came up with his law of universal gravitation, which is what we're talking about today, Newton was able to make sure that he was able to confirm that he was onto something because he was able to use this law that we're learning today to predict Kepler's laws. He was able to derive Kepler's laws from his own new relationship here, the law of gravity. Now, Kepler, when he did his work, Kepler was only describing the way the solar system behaved. He was not trying to explain it in any way. Whereas Newton came up with a theory of why these things actually happen. And again, Newton could be sure he got it right because when he started crunching the numbers in his new law of gravity, he was able to get the results shown by Kepler in Kepler's laws. Okay, so Newton was thinking about gravity and what factors affect gravity. And just from our own experience, you probably know that masses matter. So if two objects have more mass, they attract each other with more force. Likewise, distance also matters. If the two objects are farther apart, there's less gravity. Or conversely, if the two objects are closer together, there's more gravity. So more mass makes more gravity, and closer together makes more gravity. Now, here's the law that he came up with. And in this format, I can't really go into the whys of it too much, but here it is. You will probably want to pause this before I move on to something else so you can write this down because you need to know this. Okay, F sub g. So this is the force caused by gravity. So this little g here is a subscript, meaning it's a particular type of force. This is not F times g, it's just F sub g, meaning the force of gravity. Equals big G, we'll get to big G in a moment. These are the two masses, M1 and M2. So the mass of the first object and the mass of the second object, and those are always in kilograms. And then R is the distance between the two objects. Now, the reason that he used R instead of D for distance is because he was thinking in terms of orbits. So like a planet orbiting the sun or the moon orbiting the earth. And so the distance between those two is the radius of the orbit. So that's why he used an R for this. It's the radius of an orbit. But really it's the distance between the two objects. Now, remember this is important. So make sure you put this in your notes. The distance between the object is measured from the center of one object to the center of the other object. It's the center of mass. The center of planet Earth to the center of the moon, the center of planet Earth to the center of you. It's not the surface of one object to the surface of the other object. It's center to center. Okay, and then finally that brings us to big G, and we literally call it big G. This is the universal gravitational constant. And this is a kind of a fudge factor, a number that we have to plug into this equation so that when we use kilograms, and meters, we come out with newtons. Now, this is a very tiny number, 6.67 times 10 to the minus 11th. So that is 6.67, but we move the decimal place over 11 places. So it's like 0.0000000000667. Very, very, very tiny number. And this kind of makes sense because if you put two 1 kilogram masses 1 meter apart, we're not going to get something like 1 Newton of force between them. We're going to get something we can barely detect with the best instruments available to us. So big G, universal gravitational constant, very, very tiny number, which reflects the idea that gravitational forces are actually very, very tiny. Let's see. So to apply this, in class, I have you guys do an exercise where you calculate your own weight on planet Earth. Okay, and the way you do that, I would like you to do this at home. Okay, now the way you figure this out, you need to figure out your weight in newtons first to check to see if you're getting the right answer. Okay, so what you do is you take your weight in pounds. So if you weigh 200 pounds, or if your teacher weighs 200 pounds, you divide your weight in pounds by 2.2, and that will give you your mass in kilograms. So 200 pounds divided by 2.2 is 91 kilograms. Now, as you know, you have to convert the kilograms into newtons, so you multiply that by 9.8. It's actually 90.9 kilograms times 9.8 comes out to be 891 newtons. Okay, so you might want to go through that calculation to make sure you can get to this answer. And then put in your own weight, figure out your own mass, and figure out your own weight in newtons. Okay, now we're using this number to see if Newton's law of gravity will give us the right answer. So now we use Newton's law of gravity. This is the force of gravity is G times M1, M2 over R squared. So this number here is big G, 6.67 times 10 to the minus 11th. This is my mass in kilograms, 91 kilograms. That's what we figured out before. And for M2, we need the mass of the Earth, which turns out to be 5.97 times 10 to the 24th kilograms. That's a lot of kilograms. So 5.97 times 10 to the 24th kilograms. Then you need to know the distance. And remember, the distance for the law of gravity is the center of you to the center of the Earth. So it turns out the radius of the Earth is 6.37 times 10 to the 6 meters. So that's what we put in the denominator. And we have to square that number. So 6.37 times 10 to the 6, quantity squared. Plug all this into the calculator. And for me, I get 893 newtons, which is pretty darn close to 891 newtons. That's just rounding errors in some of the factors that we put into this. So yeah, works pretty well. I want you to be able to do this for yourself. If you want to follow through this calculation here to make sure you can get the same answer I did, great, but I do want you also to do it on your own. The trickiest thing about this calculation, guys, is to make your calculator work right. Being able to handle these exponents, being able to put an exponent in something and then square it and have your calculator square the whole number and not just the exponent. Yeah, so this is really an exercise in making your calculator work rather than making the equation work. But you have to be able to do this, so practice it. Okay, that brings us to the inverse square law. Let's see, these are some other ones that we do sometimes in class. We're going to skip these for now because we're pressed for time. Okay, this is going to bring us to the inverse square law. I'm going to go through this in more detail next time, but this is the short version of it. Gravity gets weaker with distance, and it actually varies by the change in the square of the distance. So let's see, we've got it summarized here. No, we don't. Yeah, this is it. Okay, yeah, oh, right. It's summarized on the worksheet that you're going to be working on here at the end. Yeah, so this is the short version of it. The worksheet that you're going to be doing today for the homework has you kind of derive this. So you're going to be doing calculations, calculating the gravitational force between different objects, and then comparing them to see how they work. To see how they vary with distance. And then you're going to look at answer some questions about them, and you should be able to derive this. This is the hope. And this is summarized on the worksheet. Okay, that's what we have for today. We'll do a little bit more with the inverse square law next time, but I do want you to do your best on the worksheet for next time.